Hey folks, so we're back with our worked examples to round out our chapter 11. We're going to start with number 25. We're going to start with number 25. It says a package of mass M is released from rest at a warehouse loading dock and slides down a 3-meter high frictionless chute to a waiting truck as shown. Unfortunately, the truck driver went on break before having removed the previous package of mass 2m from the bottom of the chute. A. Suppose that the packages stick together. What is their common speed after the collision? So we're talking about a perfectly inelastic collision. For part B, suppose that the collision between the packages is perfectly elastic. To what height does the package of mass m rebound? So I think the first thing that we want to do is just take a look at our picture here. We have mass 1, mass 2, mass m, mass 2m. Mass m starts at 3 meters above the ground. So we're already thinking, if I'm thinking about the velocity, obviously there's going to be a collision here. But if I'm thinking about the velocity, the incoming velocity of mass 1, I really need to actually take a step back and say this is an energy problem first and foremost, and then it is a collision problem. So the first thing I think we need to do in both of these cases is to solve the really quick energy problem of how fast is mass 1 going as it hits mass 2. So I would say this is an isolated so this is almost our pre-problem here. So in an energy sense, we are isolated in energy. We'll talk about isolated in the collision in just a second. But we're isolated in energy, which means delta E equals 0. What do I have initially? Well, I'm not starting with any kinetic energy. I only have potentials, so mgh equals, what do I end with? If we say that we started with some potential up here, we're going to have no potential down here is what we're going to say. We only have kinetic energy, so 1/2 mv squared. Surprisingly, not knowing m does not hinder us. We can still solve for a velocity here. Our velocity is going to be square root of 2gh, right? Or in other words, square root of 2 times 9.8 times 3 meters. If we actually work this out, where's my calculator? We got square root of 2 times 9.8 times 3. Close that square root. I get 7.67 meters per second. So that's your incoming speed, regardless of which part of the problem we're working on. That is our incoming speed of mass 1 to mass 2. So let's actually start the problem in earnest now. For part A, we're saying suppose the packages stick together. So we're saying that this is a perfectly inelastic collision. Perfectly inelastic. Is this an isolated scenario? I would say yes. I think this is an isolated collision. There is no, again, whenever we think about non-isolated collisions, we're thinking about interactions with a wall, interactions with a ceiling, interactions with a floor, interactions with the ground, right? And I don't think we're colliding with the ceiling, the ground, the wall. We're colliding with these packages, so I think that we are isolated as well. Right? These are two separate scenarios. We have the collision here, and then what type of collision we have. Or I should say the system, and then the collision. And I can't spell today. Collision. There we go. And it does have 2 L's. Gosh darn it. So, it's isolated. That means delta P is conserved, or I should say P is conserved, delta P is 0. It's perfectly inelastic, so they have a final VF that's shared, and that's what we're after. What's the common speed after the collision? So I have M1 coming in times V1I plus M2 times V2I equals the sum of M1 plus M2 times VF. So this contributes, this incorporates our isolated scenario. My initial momentum is equal to my final momentum. And then I'm also incorporating the perfectly inelastic collision with this shared VF. Now the other nice thing is our M2 VI2 or V2I is 0, right? This is at rest initially. It's initially at rest. So this actually is really convenient. I can say that M1 V1I over the sum of M1 plus M2, that is our VF. So I have I need to actually substitute M's in. I have M V1I. Well, it's actually, if we're substituting everything in, let's substitute 7.67 meters per second divided by M plus 2M, so 3M on the bottom. M's are going to cancel. And so I have 7.67 divided by 3. I get 2.56 if we're rounding meters per second. And the accepted answer in the back of the chapter is 2.6 meters per second if we're rounding to only two significant figures. So I like this. This is our perfectly inelastic collision. Part B switches things around and says, suppose the collision between the packages is perfectly elastic. It's perfectly elastic. To what height does the package mass M rebound? So part B is a little trickier. Part B is going to make us rely on our very specific scenario that we talked about in elastic collisions in that lecture, that video lecture that talked about a very specific elastic collision. But do we satisfy that condition? Well, initially our secondary mass is stationary, is 0, and we're only coming in with some initial momentum in the first mass. I think that actually works for us. So that means that we can use our expressions that we derived. V1F is equal to M1 minus M2 over M1 plus M2 times V1I. And then we also have V2F is equal to twice M1 over the sum M1 plus M2 times V1I. So these expressions were not derived right now. We derived them in another lecture video. We didn't really derive it in that video. I basically told you to look at the lecture notes in that video, but we talked about how we could interpret the results from that derivation. We want to use this V1F here to solve our secondary energy problem. To what height does the package mass M rebound? So we're basically doing our pre-problem in reverse. What is V1F, and how much height does that translate to? So if we solve for V1F, V1F is equal to M minus 2M, so that's negative M over 3M times V1I, so that's 7.67 meters per second. M's will cancel, so I'm taking a negative third of that, 7.67 divided by 3. Oh, that's the exact same thing that we had before, right? That's the exact same thing we had before, except it's negative now. So we go negative 2.56 meters per second. That's assuming a perfectly elastic collision. And what height does that amount to? Well, if we go back up to what we had here, right, I'm saying that I have mgh, m's are going to cancel, equals 1/2 v squared. So if I say h is equal to 1/2 v squared over g, I think that looks about right. Let's plug and chug. 0.5 times 2.56 times 2.56 divided by 9.8. I get a total height of that's not right, is it? No, it isn't. Oh boy, man, I I don't know what the heck I did there. 0.5 times 7.67 times 7. No, man, 2.56 times 2.56. Send help. Divided by 9.8. There we go. There we go. I get 0.33 meters, or we can say 33 centimeters. Right. So it goes up only a fraction of the initial height, and that kind of makes sense. Mass 2 isn't huge compared to mass 1. It's only twice the mass. If it were 1,000 times as massive and it was a perfectly elastic collision, we could expect mass 1 to maybe get up to like 2.9 meters, because it would retain all of its momentum, just opposite, right? And then the mass 2 would barely move. But that's not this problem. This problem has relatively equal masses. So I like this problem because it gives a sense of a perfectly elastic collision. What about a perfectly inelastic collision? A perfectly elastic collision. So I like this problem a lot, and it incorporates some energy concepts into it. So if you have any questions with this, come talk to me. Shoot me an email. Come to an office hour and be happy to talk about this. All right, have a good one. Bye.